Okay, so hello guys, in today's video. Today we will talk a bit about RPM measurement of DC motor. So what I will be presenting to you today is a small module that we'll see in a second, where we have a motor, a small coupling to the potentiometer, and photo sensor for measuring RPM. So this is how the whole circuit looks like. On the right side we have a small infrared / light receiving circuit that was presented on my channel in infrared and electronic projects video. Here we have a 12 volt LED light bulb. Here we have a motor that is like a 5 volt motor. Here we have 9 volts connected to a potentiometer. It can be 9 volts or more, but it will be 9 volts because this is the same power supply voltage like here. And then we will be measuring stuff and some calculations that will be done later. So let's see the module. So this is how the module looks like. It's mounted on a CD cover, plastic CD cover, and what do we have here? We have DC motor there, which is connected through this normal switch that you can switch on and off. It is connected to these two wires that you're not able to see. Here is a red one, here is a black one. Then here we have a small infrared / light receiver, just a photodiode driver. Here we have the photodiode, here we have the output of the sensor, and here we have a power for the sensor. Here we have the potentiometer with a small little gear set there, and here we have the power wires here that come out of the potentiometer. Here we have the small 12 volt LED light bulb that is connected to a DC jack there, so I can connect it to 12 volts, and it's covered up with tape so it won't blind us with the light. And here I have written 18, 1 to 18, because this is the ratio that here we have, because we have one here, like one, I don't know how to call it, like one transmission here, because it just comes out of the motor straightly here. And here we have 18 holes on the full, on this disc that rotates. So one full revelation will be equal to 18 pulses of this LED, because it's a pretty narrow, not LED, photodiode, so it will be it's a pretty narrow LED, so it should pulse 18 times for one full revelation. But here we have 9 here and 36 on this gear. So the transmission here is 9 to 36, which is 1 to 4. So that's how here we will be calculating the whole thing. It decreases 4 times. Okay, so right now we have everything connected up. Here we have the module. Here I have some power connections down there. DC jack for the motor. The module here, my power supply is set it to 9 volts, and it delivers power to motor and photodiode driver. And on the right side we have the potentiometer, which is connected to 9 volts too. So the first measurement that we will do, which is on channel 1 on my scope, will be the measurement of the potentiometer. So let's turn on the motor. The thing starts to spin, as you can see, and we have a very nice waveform. The potentiometer is weared out a bit, so that's why the whole waveform doesn't look so nicely. But potentiometer rotates, it's modified, so there is no stop mechanism, so it doesn't stop. It can turn without any stop, and it lets us to rotate it with, for example, a motor. It's a continuous motor and continuous potentiometer, so it doesn't stop. So in result of that, it just rotates, and then it jumps in a track from the end of the range of the potentiometer to the beginning, and it starts again and again and again and again. So this is what we are seeing here. Increases somehow resistance, Here we have like a small little break in the trace, crack in a trace, then it goes to the beginning, starts all over again, and this is how it basically works. Yeah, that's basically how it looks like. So now we can turn off the channel 1, turn on channel 2, set the triggering to channel 2, and right now what we can do is connect the 12 volt LED. We can see that some noise appeared there, which is just a, I believe, high frequency noise. Probably, yeah, as you can see, it's just noise of the power supply or something like that. It will be more clear in a second when I will start up the motor. So we start up the motor and we can see the sign, as you can see. Of course, it has a bit of a harmonic because here we have a little wobble on the other side caused by the potentiometer, and because it's not ideal. And this is our second waveform, which is sine wave, as we can see. So let's get right now to some formulas and calculate the triggering based on that. Okay, so this is basically what we saw on scope. We have some period here, and some period, full cycle we can call it, here. In this place, where we have ratio to 1 to 18, which is this coupled to the potentiometer, we have 1 to 4 coupling, sorry. Here we have the frequency of this waveform, which is 4.95 Hertz. Pretty slow, isn't it? And then we multiply it by this number, we get 19.8 true revelations on the other side of the gears, on the transmission, on the other side of the transmission. So we calculated, this is the right number on the right side of our gearbox. Then we have 19.8 times 60 because we want revelations per minute. Here we have revelations per second. So revelations per minute in this case are 1.1 thousand RPM per second, 1.2 thousand RPM per second. Here we have frequency of this waveform, and here we had 1 to 18 coupling between here, and this kind of like a shade kind of disc is 1 to 18, so full revelation will be 18 revelations here. So here we have 367 Hertz. We divide it by 18 because in this case it will be slower on the other side of the gearbox of the transmission. 20.42 we got, and then we multiply it by 60 because we want revelations per minute, not revelations per second, and we have 1.2 thousand. So here I have a bit better, I think, picture. So here we have the motor, here we have the coupling, here we have like the gearbox 1 to 18 ratio from this side to this side 1 to 18. So this moves 18 times faster than this side. So that's how we can calculate it. Then on the other side we have 1 to 4 gearbox or transmission, as you wish to call it. So this moves 4 times slower than this one, and this one 18 times faster. So measurement methods, we have two types of measurement method here. So we have optical one, which is this one. It should be more accurate in theory. Then we have the potentiometer one, which is B, and RPM measured by those method is this. So 1225.3 RPM with the optical method, and B, which is 1188 measured by the potentiometer method. So in summary, I written that both methods are pretty good and accurate because the difference in between of them is only 3.14%, which is roughly 3% difference. So that's everything for this video. I hope you enjoyed it, and see you the next time.